All right, let us talk about the pre-quiz. We are talking. I have audio. Class. So for these ones here, the first one is moving loops. The idea is that the magnetic field sits still. The loops are moved into or out of the magnetic field, right? And remember, the rule is that if within the loop we gain something, we oppose it. If we lose it, we replace it, right? So here, the first one, that box is going to gain out of the page. Yeah, are we all clear on that? It's going to be moved into a place where there's out of the page flux, so therefore the inside of the loop gains out of the page. If you gain it, what do? You oppose it, right? So to make flux into the page, that I would oppose out of the page, right? You go clockwise. Are we good on that?
Oh yeah, we're good.
Right. This one here, we're pushing it into a place where there's into the page, so we're gaining into the page.
Wait, do we want that there?
No, we don't want into the page. It's never been here, right? Okay, so what do? We oppose that by making out of the page. That's why it's anti-clockwise. Yeah? And the Brits are, by the way, going to use clockwise, anti-clockwise on you. So I just want you to see that before the test and go, what does that mean? Probably you'll figure it out, but maybe you'll spend 30 seconds that you could spend like scratching yourself or something. You know? Okay, better we use, right? Okay, so here we are pulling the loop out of this thing, so we are losing out of the page, correct? Because we don't want that. It's always been there. Always been out of the page, right? As long as I can remember. Okay? So if you lose it, what do? You replace it. So as this thing goes out of the page, it makes its own flux out of the page. If you're not going to provide it, I'm going to make my own, right? Yeah? Okay? Here you are losing out into the page, right? No. We always want into the page, right? Okay? So if we lose into the page, we create our own flux into the page. Yeah?
Wait, I don't get it. How do you know it goes that way?
Oh, because remember, the way the flux works inside a loop, and that's all we care about, right, is that you put your fingers in the direction of the current, your thumb is the direction of the flux inside that loop. Also, by the way, where the North Pole is, because that's what a North Pole is. It's something that has flux lines coming out of it. Yeah? Right? So for this guy here, we're moving it from in the magnetic field to out of the magnetic field. So we lost into the page, so we create our own flux into the page by going this way. Yeah? So, yeah, on the test, I think there's like, I've got like one bar of these and then another one of the...
So whichever way it's pulled out doesn't matter?
Doesn't matter, yeah, that doesn't matter. Just into or out of, that's the important thing, right? I just draw them differently because, I don't know, I got bored. Okay, so this one here, now the loops aren't moving, we're just increasing or decreasing the flux, right? So the magnetic field increases, we gain out of the page. How do we fight that? Go into the page, right? Here we lose into the page. Right, it's decreasing, so we're losing it, so we make our own into the page. If you're not going to provide it, we'll provide it. Yeah? Yeah?
Wait, who are you?
I don't know what we are, you know? Okay, so here we go. We've got a magnet approaching. Do we want that magnet to approach? No! Never been here. Never had a North Pole magnet here. We're not gonna, as long as right? So we make the current flow this way. We make a North Pole to oppose that North Pole. Yes? And we resist the motion, right? Do we want the South Pole?
How do you know, like I know it's down, but it's also up. Like, how do you know?
But here it said the front of the coil, right? So on the front of the coil, it's going down the front of the coil. Yeah? Okay. Okay, here the South Pole is trying to leave town. We don't want it to leave town. How do you induce it to stay?
Why don't you want it to?
Present it with a North Pole. Yeah? So again, it's going to go down the page, or you can just give it tax incentives to stay, right? That also works, but that's like, social science or something. Okay. Now these guys...
Oh yeah, wait, will we get hurt for that if we write taxes?
No, not so much. That's for another class, right? Okay. Now for these guys, the way these guys are supposed to be interpreted is that this is the wire. When we talk about the current, we're talking about the current in this wire. Okay? So here the current in this wire is going to increase. Remember, the magnetic field around the wire is, well, it's this way. Thumb in the direction of the current, fingers this way. Where that loop is, which way is the flux? Out of the page, correct? Okay, so we are increasing out of the page. Do we want that? No, so we make flux into the page. Yeah?
Yeah.
So figure out which way. Now there's an extra step. You got to figure out which way the flux is, and then we're back to where we started, right? So here, the flux where that loop is which way? It's out of the page, and we're losing out of the page. We're losing out of the page. So what do? We replace it. We create flux out of the page with our own current. Yeah? Okay? And then these guys, it doesn't really matter whether it's inside the loop or it's outside the loop. That just doesn't matter. Okay? So for this guy, the outer loop, the current is increasing. Okay? So this outer loop is making more flux out of the page, correct? Okay? Do you like that? No. Okay, the federal government should not tell the states what to do, right? And so what do we do, right? Well, we make flux into the page. The outer loop imposes flux out of the page on us. So here in Dade County, right, we make flux into the page, right?
Right.
There we go, right? Okay, how about here? This thing here is trying to make all this flux out of the page, and it's increasing flux out of the page. Do we like that? No. So we make flux in this outer loop. We make the flux into the page, right? And then this guy, this is just this rule, I believe. I don't know any other way to do it, right? So we go like this. The velocity is, for that first one, this way. Magnetic field is out of the page. Which way is the positive charge in the wire forced? Down the page, correct? Yeah? Okay. Then for this guy, it's the positive charge is being forced down. Magnetic field's into the page. It's forced to the right. Okay. And then this one here, this loop is getting, this thing is sliding along that. This U-shaped thing is sitting still. This guy is sliding along that, right? And so that is increasing the flux out of the page. Do we like that? No. So we make flux into the page. We oppose the increase. Yeah? Okay. And then, because this area is getting bigger and bigger, right? As we slide that wire that way, this little window here gets bigger and bigger. Because the U-shaped thing sits still, leaves it behind, right? Okay. Here, we're making that little window smaller, yes? So we are losing flux into the page. So what do? Make our own flux into the page. If they're not going to give it to us, we're going to make our own. Yeah? Okay. And then thank you, Mackenzie. I'm just either randomly thanking you or I thought you did a nice job. Where's the pen that goes with this thing? It's a pen. We got a pen without a cap. It's an emergency. Okay, so the next one is the let me get a little tighter on the board here. The approach of a magnet, right? So we've got this loop of wire here. A North Pole magnet is going to approach. Do we want that North Pole magnet to approach? No, we don't. Right? So how do you keep a North Pole magnet from moving into town? Present it with a North Pole, right? So as this North Pole approaches, current is going to go anti-clockwise to make it not approach. Yeah? It's going to make a North Pole that it sees, and it's like going, oh, North Pole magnet, don't like that. Right? Okay. So it's going to go anti-clockwise.
Yeah, there you go.
Right? And then it goes from something to something in 0.621 seconds, 2.5 meter radius, right? So this is an NBA over T kind of a problem, right? N is 1. B is the thing that's changing, so it's 0.249 minus 0.192, is that what it is? No, 142. I'm like a dyslexic's dream here, right? Okay, and then it's pi times 2.5 squared, right, divided by 0.621.
Wait, where isn't it just going to be the other way around? There's subtraction and one's supposed to be negative.
I don't think so. They're both into the page. They're both into the page, and I just in these things ignore the minus sign kind of thing. But they're both into the page. If one, by the way, was out of the page and one was into the page, then you'd have to do something like an addition, right? Subtract a negative or something like that, right?
Yeah.
Okay. So just be careful, watch for that. I don't know that I tweaked that on the skill set, but look for it, right?
I got the same number and everything, but
Here's what I'm doing. I'm going final minus initial, which always gives you like the change. Okay, so that times pi times 2.5 squared divided by 0.621. And you get 3.38 volts, is that right? Right. And then it asks all these questions, and you're like, what's going on here? You know, which way does the current flow if the loop has a resistance? And then it keeps asking these questions.